Welcome to Microsoft Excel with EJD. In this video, I'll be talking about t-test with Analysis ToolPak. We've been doing a lot with Analysis ToolPak. We've talked about descriptive statistics, histogram, regression, correlation, random number generation, sampling, and so on and so forth. So we're still going on with this as we consider the idea of t-test with Analysis ToolPak. Interestingly, when I taught statistics, I think I have about 25 or 35 videos on statistics. So you want to check the playlist on statistics on the channel. I explained the mathematics behind this whole t-test thing. So you can get the math idea from there and then relate that with the simplicity of implementing that in Excel. So understanding the maths behind it is going to give you a lot of clarity, and then knowing how to do it with Excel makes you see how simple it is to implement what you would have learned then, no matter how rigorous the mathematics can be. Okay, so talking about the t-test with Analysis ToolPak, t-test is the statistical method used to determine whether there is a significant difference between the means of two groups. So you have group one and you have group two. Those groups can then vary depending on whatever, as you're going to see. So you have group one and group two, and you have data for each of the groups. So you take the mean of this, say this is mean one, and take the mean of this is mean two, right? The second mean, okay, mean two. So what you're trying to test is whether there's a significant difference between the means of two groups, which may be related in certain features. So the null hypothesis is that there is no significant difference between mu1 and mu2. So we can just simply say mu1 is equal to mu2. There's no significant difference, right? That the difference between them, or of course, the other way to look at it is that mu1 minus mu2, the absolute value is equal to 0. Because there's no significant difference. So Microsoft Excel's Analysis ToolPak provides a convenient way to perform various types of t-tests without needing complex manual calculations. It can be quite complicated. The calculation for t-tests can be quite complicated. Not so complicated though, but it has a formula that you have to follow step by step. Now, having said all of this, the next thing you want to pay attention to is the fact that the Analysis ToolPak offers three primary types of t-tests. Of course, these are the types of t-tests. Okay, so for the types of t-tests, you have, first of all, the paired t-test. So on the YouTube channel, what I've done there is I did all of these tests and I gave you their Python codes. So you have paired t-test for dependent samples. So the samples depend on themselves. It's like the data is coming from, it's more like maybe before students were admitted into a school, you give them a particular math test. And then after being taught in the school for one semester or two semesters, then you give them the same test and to compare their performance on the test. And that way you want to measure how important, how impactful your teaching has been on the students. So that's a very good example. So you have conducting the same test twice on the same person or on the same, yeah, something like that, on the same set of students, basically. So that's where you have paired t-test. And that's for dependent samples. Number two, you have the two sample assuming equal variances. Assuming equal variances. Assuming equal variances. In that case, you have independent samples. So it's more like you have scores from two independent groups, right? So you have a group of students. Maybe in this case, now maybe you have still using the same academic example, right? Maybe you carry out a test on students in science class, and then you carry out the same test on students in the technical class, if there's anything like that, and then you're comparing whether the mean between their scores is the same or not. The same null hypothesis subsists that mu1 is equal to mu2. Of course, automatically H1 would be that mu1 is not equal to mu2 for two tailed tests. And for one tailed test, you can have mu1 is greater than mu2 or mu1 is less than mu2, depending on the kind of test you're interested. So this is, I think this would be right tail test and this is left tail test or whatever, like that. Okay, mu2. So all of that go. All of those actually go actually. Number three, you have two sample. So you have two sample assuming two sample assuming unequal variances. Assuming unequal variances. And of course, this is still talking about independent samples. And basically, the idea of independent samples is the fact that you are conducting the same test on two different groups that are exclusive of themselves, basically. So those are the three types of t-tests we have in Microsoft Excel Analysis ToolPak. Of course, talking about the paired t-test, right? Talking about the paired, look, I thought I changed this. Talking about the paired t-test for dependent samples, right? A paired t-test is used when you have two related or matched samples. So this often arises when you measure the same subjects before and after a treatment or under two different conditions. So it's either, just like I gave the example before you admitting a group of students to your school, you give them a test. After teach them for a semester, you give them the same test again to see their performances, to measure how impactful your teaching has been on them. That's a very good example. Another example is that, okay, you give them the test in the morning and you give the same set of students the same test in the afternoon. You want to see the impact of the period of day, the time of day when they took the test on them. Something like that. That's the very good example of paired t-test. Okay, so the purpose is to test if the mean difference between paired observations is zero, like I stated before. That's the purpose. So, and the example is comparing student test scores before and after a training program, like I've been saying, and the data requirement, two sets of related data, e.g. before and after scores, arranged in two columns, right? We are going to see that very soon. Then how it works, the tool calculates the difference for each pair, then tests if the average difference is significantly different from zero, right? So we want to see if the average difference is different from zero. Of course, we have metrics for measuring how this works, okay? The key assumption is that differences are approximately normally distributed. So we assume that differences are approximately normally distributed. So if you want to write something for this, you want to test if the mean difference, between paired observations, is zero. Okay, so just like I said, right, administering a test on the same group before and after a training or in under the same group under different conditions. That's why it's dependent. Now let's go ahead and talk about two sample assuming equal variances. Two sample, sample assuming equal variances, and of course, that's for independent samples. The idea of independent is that you have two different sets of students taking the same test, and you're trying to see if their scores, if the mean of their scores is the same or not. So this test compares the means of two independent groups when you assume the variances of the two populations are equal, and that is called homoskedasticity. Okay, that this this compares the means of independent independent. You need to understand the condition to do the right kind of test. So this compares the means of two independent groups. Okay, when you assume the variances, of the two populations So now variance is coming into it. The variance of the two populations are equal. Are equal. So that talks about homoskedasticity. So equal variance talks about homoskedasticity. So the purpose is to test whether two independent samples come from populations with equal means. And the example is comparing average heights of males versus females. You know, males and females are exclusive, right? Mutually exclusive. So you want to test their heights. So that is a very good example of independent samples, and you want to see how the heights compare. So the data requirement, you need two columns representing independent samples. The key assumption is that both populations have the same variance. How it works, the two pools the variances to get a common estimate and compute the test statistic accordingly. So if you check my teaching on statistics under hypothesis testing, you'll actually see how you get to compute that, and you need the standard. I think it's called standard error or something like that for each data set, and use some serious formula like that, and you go on with that. Okay, let's talk about the third type, which is two sample assuming two sample assuming unequal variances. Two sample assuming unequal variances. Of course, still talking about independent samples, and here we talk about the Welch t-test. So we have the Welch t-test here. So this is used when two independent independent samples are assumed to have different variances. So if same variance is known as homoscedasticity, different variances will be known as heteroscedasticity. Heteroscedasticity, like that. So the purpose is to test whether two independent samples come from populations with equal means without assuming equal variances. Example is comparing effectiveness of two different fertilizers on plant growth when variability differs, right? Then data requirements, two independent samples in two columns. How it works, the tool uses a modified formula adjusting the degrees of freedom to account for unequal variances. Okay, so let's see how to get this done practically and get over with it. Now, imagine that we have this Excel. So I have Excel sheets prepared to talk about these things now. So the first one, of course, is the paired t-test, where you have a score before and score after for a group of 100 students admitted into a training program. So to see how they perform before and after the training, so let's look at that now and see the kind of let's see how their performances compare. Okay. Um, let's go for that now. Now, again, before to get this done, right, you need to check if you have the analysis toolpak add-in and you come to data. If you see this analysis here, it's good. What if it's not there? For instance, if you are going to remove this now, let's see, you just go to file, you come to options, then you click on add-ins, and then you come to this manage area, Excel add-ins, and you click on go and uncheck this. So take note, we have this here now. Once you click OK, it disappears. And then with that, you cannot use the analysis toolpak for all this analysis you've been doing. So how do you get it back? Go to file again, come to options, click on add-ins, then come to the manage, click on go, and then check the analysis toolpak and click OK. So now you have it back. Then you can go ahead and do your t-test. So don't forget, the first one is the paired t-test for dependent samples. Okay, so you click on data analysis. So once you click on that, then you look for t-test. So you have many things, right? So you go for t-test. So here you have t-test for paired two sample for means. Okay, so you click on that now and say okay. Now it tells you variable one range. So that's scores before now. So you can click from the very beginning to the last. Okay, or you can also type the address directly. That's A1 to A101, but you lock it down using the $sign. So for the second set of variables, you also come here and highlight. You can then highlight everything all the way down, more like you're copying or something like that, just to tell the cell address. So now you have A1 to A101, then B1 1 to B101 for variable range 2. Then we have labels there for sure. Hypothesized mean difference. We are saying that there's no difference between mean 1 and mean 2, right? And that's 0 here. That's what that simply means. The output range, let's say, I have A and B. So let's keep C and D, or let's even skip only C and go to D. So we just want want our result to be outputted at D1. All right. So once all of that is done, I think everything is in order. So we just click on OK, and then it spews out the result. And that is what we have right here. Okay. So how do we interpret all of this? You can do some formatting to make the results okay, let me leave this and then just come here and centralize all of this. So we have home and then this like that. Okay, so how do we read this? So you should be able to interpret this normally, because as you're going to write your report, you need this. Of course, you can see we have mean for score before and score after. It's more like just taking average of the score before. All right. So we have the mean. That's what that simply means. So it is the average of each sample. So the average score before is 72.23. The average score after is 75.05. That's already giving us a signal of better performance after the training program. Then we have the variance, which is a measure of spread in each sample. So the spread in the score before is bigger than the spread after. That means that, most of the students, because of the training program is making them get, scores that are close to themselves. All right. And then, of course, we have 100 observations for each. That can be taken for granted. That's number of data points. Then we have the Pearson correlation for pair t-test, which shows how related the pairs are. And we have 0.99. So the score before and score after, they are strongly correlated, meaning that the higher the score before, the higher the score after, basically. Then we have the hypothesized mean difference. The assumed difference to test, which is often 0. We are saying that mu1 minus mu2, the sample for the score before is the same as the sample for the score after. Basically, that's the hypothesis. Then we have the degree of freedom, which is used to determine the critical value of t, right? Then we have t stat, which is minus 50. So t stat in this case is the calculated test statistic, and it's here minus 50.59, like that. And then we now have probability t is less than or equal to t for one tail. And so this is very small. This is 72 zeros before you get to the 74969, like this. So this is roughly 7.5 times 10 raised to minus 73. That's plenty zeros. That's very, very small, right? That's the probability of observing the data if the null hypothesis is true, right? For a one-tail test. So then the critical for one-tail test now, that's something you read from the table. So the critical one-tail and two-tail is critical values for rejecting null hypothesis. So it means that if these values can be greater than the critical value, then automatically you have to reject the null hypothesis. But you can see in the two cases, for either two-tail or one-tail, the probability is less than the critical value in each case, because these are very small values, 0.00000 all the way down. Then you have this ones to be 1 point something each. So it means that there is significant difference, basically. So we do not reject the null hypothesis because these ones do not exceed the probabilities do not exceed the critical value. So we accept that there's significant difference between the test before, the score before and score after, like that. All right. So that's for paired t-test. So let's go on to talk about the two sample t-test assuming equal variance. Same procedure. Go to data. So in this case now we are saying maybe we are taking, let's say we are running the same test on class 1 and class 2, sample 1, sample 2. That's what we've called them here. And then we just go on to this place. Mind you, we are no longer going to use pair 2 sample for means, because we are talking about two groups, two different groups. Now, in the first case, we have the same group administer the test before and after, but here we have two different groups administer the same test. So we say two samples assuming equal variances. So because of that's talking about homoscedasticity. So in this case, we just go ahead and say, okay, again, variable for range 1, you go for sample 1, again, highlight all of that down to the last, or you can just type it out in that box. Okay, it goes to this, and then we come here and then do the same thing. Okay, so sample 2 now, we have all of this. down to the last. Okay. With that done, then we come to the hypothesized mean difference, which is usually taken to be zero. If you have some other values, feel free to put it, but it's zero by default. So we have labels. So in this case, now we need an alpha. We need, I think this is called a significant level or something like that. Then the output range, since we have A and B, so I'll just jump to D. So I click on this and I just click. Then I want the result to come here. So you could actually make the result go to a differentiable. I mean, it's something cool that can just fit in here. So I just, after all of that is done, just click OK in one blow. I mean, if you want to do the maths for this, it's a lot of stress, but Excel has made it significantly easy to handle, right? So we now see all this information about sample one and sample two. As usual, I want to format, so centralize like this. And then, of course, I think that suffices. And then we can try to do this to make things a bit tidier. So, of course, you see t-test two samples assuming equal variances. So, of course, we have the same thing. The mean for each 72.65 for the first group, first sample, 74.64 for the second sample. Variance is 65. So, very close, but I mean, the variance for the second sample is smaller, 100 observations. The pooled variance is now 65.68 for all the, so that's where you have something like S1 and S2 and all that. If you check the actual maths behind this under the statistics playlist for under t-test, that follows this. So hypothesized mean difference, of course, is zero. The degree of freedom is 198. How do we get the 198? We have 100 samples in two groups. So that's like group one, that's N1 plus N2 minus 2. So that's 100 plus 100, 200 minus 2, that's 198. That's how we get a degree of freedom in this situation. So you have the t-test to be minus 1.73. So if the probability for one tail is 0.04, of course, which is still smaller than critical value. For two tail, it's 0.08 something, which is still smaller than the critical value. So in that case, you accept the null hypothesis that there's no significant difference between the mean for these two different samples. Then that takes us to the third group where we talk about two sample t-test assuming unequal variance, where we talk about heteroscedasticity. Again, same story, go to data, come to data analysis, then of course move down to t-test for two sample assuming unequal variances. Click OK, same procedure, then highlight sample one all the way down to, okay, maybe I should just use the addressing thing this time around. So you have A1 to A101. Oh, this has made it easy for us. So then I come here, then I have $B $1 full colon $B $101. That's where the variable range 2 is. And then I come here, the hypothesized mean difference is 0. If you have some other value, feel free. In case your question says you want to test that the mean difference between 1 and 2 is 1, feel free to put 1 here. So, but usually we say 0. The output range, I also want it to be at D1. So I log that down. So $D $1. Of course, with all of that done, I can just say okay. And then we have our results spewed out right there. Okay, so we have all of this. We have all of this. So let me shrink that a little bit. So so we have sample one, sample two, bring it down this way, and then we can do a bit of formatting to make it more readable. Okay, so the mean, of course, mean for the first sample is 61.39. Sample two, it's 7.64. Variance, okay, this one is also spread out, but this one is way spread out because we have 38 here. Same of the number of observations. Hypothesized mean difference is 100. Degree of freedom is now 141 because definitely this is following another kind of calculation. And then the test statistic is minus 38 points, all of this. And then here you have very small probabilities, right? Very small compared to the critical value. So in this case, again, we also uphold the null hypothesis that there is significant difference between the mean of the two samples, even for in the case of heteroscedasticity. So with this, using Excel's, okay, well, we can do a kind of when to use each t-test type, right? So for paired t-test, you have related samples. the variable variance assumption, there's no variance assumption at all. So common use before and after or matched pairs. Then you can have two sample equal variance. That's student test. So here you have independent samples with equal variances. Used for similar groups with equal variability. And then for two sample unequal variance, the wedge test, you have independent samples and then you have unequal variances. And the common uses are in different variability and safer general use. Okay. In summary, right, using Excel's analysis toolpack to perform t-tests provides a fast and reliable way to analyze differences between two groups or conditions, whether testing paired data or independent samples. The tool simplifies the complex calculations and provides key statistics for decision making about your hypothesis. So, I mean, you can do all these tests of hypothesis without uh, dropping a sweat, like they say. So, feel very free to get acquainted with this and enjoy away. All right, with this, I come to the end of this video. Let me know how helpful this is for you. And if there's something you'd like me to try out, feel very free to let me know. If you have not subscribed, of course, you're missing out already. So please go ahead, subscribe, hit the notification bell, so that you can always get alerted each time a new video is released. You can become a member of this channel. Just click on join, and then you get some special privileges by becoming a member. Feel free to avail yourself of that. Be sure to like, share, comment, so that more people can have access to this great content I have going on here. Till I come your way again, keep doing data right. Bye.